Oh, Mr. Nice.
Yes, sir.
That makeup test you gave
Mm-hmm.
in your email, I submitted it yesterday, but your email says it was due yesterday, the 22nd. But on your assignment, you put it due 24th. I was just curious, what was the actual?
It's due the 24th, but let me check.
Okay, well, in the email, you put 22.
Oh, the email,
Yeah, and then I saw the due date on the assignment was 24.
let me see.
I was just curious about it.
Oh, yeah, okay. Should be the 24th. So you still, I mean, if you want to, you can,
Go back and revise it.
yeah. All up to you. Let me check. Okay, right. 24th. Okay, let's take roll. Yeah. Okay, so Marat, Bessie,
Here,
Burke, Kane, Dunlap.
Here.
Gallegos, Ted.
Here.
Irvin.
Here.
Medina Kylie, Medina Manuel, Menisi.
Here.
Marcier is here. Oh, and Kane dropped in. Kane is here. Olano, Richardson,
Here.
Sieg. Here. Tillman.
here.
Venture Pagada, Weflin, and Wright. Okay, so we're going to finish up on this chapter. There's really only one other topic to discuss, and that has to do with the equilibrium or equilibria that's associated with the formation of complex ions, right? So firstly, we have to start off with a definition of what a complex ion is. A complex ion is basically a collection of atoms where the central atom is a cation and it's surrounded by molecules or anions. All right, so a good example of this is shown here, where you have the cobalt 2+ ion will combine with 4 chloride ions to form this complex. So this complex here is simply a cobalt ion surrounded by 4 chloride ions. So that forms one unit. So that's called a complex ion. And as you can see, the formation of this complex ion is a reversible process. Make this full screen. It's a reversible process and therefore will eventually achieve equilibrium. And therefore, the same discussions that we have had about different systems in chemical equilibrium will apply to the formation of complex ions, right? In fact, the equilibrium constant associated with the formation of complex ions is called the formation constant of that ion or the stability constant. And that is symbolized by Kf, right? So Kf is basically the formation complex of a complex ion, or formation constant of a complex ion. And what you'll find is that the greater or the larger the magnitude of Kf is, the more stable the complex ion is. And what you're going to find is that most of these ions, if not all of them, are very stable, right? In fact, we have a list here of some complex ions. And if you look at the formation constant, you see that these numbers are huge, right? So this is like 15 million. This is 1.0 times 10 to the 21, 1.0 times 10 to the 25, and so on and so forth. 5.0 times 10 to the minus 10 to the 31, 2.5 times 10 to the 41, and so on. So all these numbers reflect the fact that all these complex ions that are formed as a result of a cation combining with either a molecule or an anion, all these complex ions are very stable, very, very stable, all right? So that's basically the introduction to formation constants of complex ions. Let me go directly to the next assignment question. Yeah,
Did you have extra copies of the assignment file?
I think so. Or I thought so. Oh, wait a minute. Oh. Yeah. Okay. Okay, so let me download this. Now. Okay, so let's look at question number 10. Oh, by the way, let me see. We did 8A and B, right? And of course, we did 9. Okay, so question number 10. It says the Fe3 plus ion complexes with the cyanide ion to form the complex ion, and it gives you the formula. It says in a 0.11 M solution of potassium cyanide, the equilibrium concentration of Fe3 plus is 8.5 times 10 to the minus 40 M, and that of the FeCN6 3 minus is 1.5 times 10 to the minus 3. Calculate the overall formation constant for that complex. So first thing I would do is write down the equation for the formation of that complex. So let me turn on my pen. So it's going to be Fe okay, so it's going to be Fe3 plus 6Cn minus, and this would be in equilibrium with the complex FeCN 6 minus, right? And the Kf value is what the question is asking for. Right? So we know, based on what we have just discussed, that Kf is equal to the concentration of FeCN 6 3 minus divided by concentration of Fe3 plus times the concentration of Cn minus raised to the 6. So all we have to do, because they gave us the equilibrium concentration of Fe3 plus, they gave us the equilibrium concentration of the complex, and they gave you the concentration of the cyanide from the potassium cyanide. So it's all a matter of putting these numbers, plugging these numbers into this equation. So above in the numerator part, we're going to have 1.5 times 10 to the minus 3 divided by, for the Fe3 plus, it's 8.5 times 10 to the minus 40 multiplied by the concentration of the cyanide, which would be 0.11 raised to the 6. And then we do the calculation. So 1.5 times 10 to the minus 3 divided by 8.5 times 10 to the minus 40 times 0.11 raised to the 6. And according to my calculations, I got 7.5 times 10 to the 44. And that's basically how that is done. Oh, wait a minute, I did something wrong. What did I do? I think I did something wrong with the math. 1.5 times 10 to the minus 3. Okay, I think I know what I did wrong. I think I did not correctly raise the 0.11 to the correct number of exponent, and then I multiplied by 8.5 times 10 to the 40 minus times 1.5 plus 10 to the minus 3. Okay, so this is incorrect. And the answer is when rounded off to 2 sig figs, 1.0 times 10 to the 41. Okay, so I'm sure 10 to the 42. All right. So that's the answer to that question. All right. Okay, any questions about this example or this question?
Yeah, when you plug in the 0.11 M per CM minus
Mhm.
in the question, like where it says KCN for the concentration.
Right. So the potassium cyanide is what provided the CN because the potassium cyanide will dissociate to form potassium and cyanide ion. Right. So whatever the molarity.
Yeah, the complete dissociation.
Yes, right. Complete dissociation. All right. Okay, any other questions about this one? Any other questions? Okay, continuing, clear this. Well, the next question is not as simple because they're talking about KSP for silver bromide. And it says calculate the molar solubility of silver bromide in water. Well, that part is easy because we know how to do that already. And then it says silver forms a complex with ammonia, and it gives the formula of that complex. And the Kf for the complex is given. And the question is asking in the A part, what's the molar solubility of silver bromide in 1.5 m ammonia, and what mass of silver bromide will dissolve in 175 ml of 1.5 ammonia? And I just realized that when writing this question here, I should have made this part A, this part B, and this part C. It's a 3-part question. So please make a note of that. I'm going to change it and upload it into Canvas. All right, so the A part, let's focus on that first. It says, you have to find the molar solubility of silver bromide in water. So of course, this would be the equation. AgBr, I'm sorry, Ag plus Br minus. Okay, so again, we're setting up our ice table. So initially you'd have none of these two. And then at equal, and then the change, I'm sorry, is going to be plus S here, plus S here. So at equilibrium, you're going to have S and S, which means that KSP would be equal to S squared, which means that S would be equal to the square root of KSP, which is equal to the square root of 5.35 times 10 to the minus 13. And when I did that, 5.35 times 10 to the minus 13, and then I find the square root of that, I got 7.31 times 10 to the minus 7. All right, so that's the A part. That's the A part. All right. Any questions so far? Any questions? Because I need to clear this so that I can move on to the B part. So let me do that now. Now the B part is asking for you to calculate the same thing, but this time in 1.5 m ammonia. All right. So basically there are 2 equilibrium reactions that we have to be concerned with. The first one is the one that we just dealt with, AgBr, to form Ag plus Br minus. And then the second reaction is the reaction where the silver ions react with ammonia. And because you have 2 ammonia molecules in the complex, you're going to have 2 NH3 here. And then the product of this reaction would be silver with the 2 ammonia molecules attached. And all of that will carry a plus charge. So we have that equation to contend with. So the KSP for this is equal to 5.35 times 10 to the minus 13. And the KF for this is 1.69 times 10 to the 7th, right? Now, this is a two-step process, which means that you can add them together to get the overall reaction. And of course, when we do that, we have to cancel out those items that are common on both sides, which in this case would be the silver ions. So therefore, the net equation would be AgBr plus 2NH3. And then on the other side, you're going to have AgNH3. Oh, by the way, there should be a 2 here. AgNH3 2 plus Br minus. So my question to you is, what would be the K for this reaction?
You multiply the.
Exactly. Would be KSP times KF, which would be equal to 5.35 times 10 to the minus 13 times 1.69 times 10 to the 7th, right? So let's do that calculation. 5.35 times 10 to the minus 13 times 1.69 times 10 to the 7. And when I did that, I got, rounded off to 3 sig figs, I got 9.04 times 10 to the minus 6, all right? So that's the equilibrium constant for the net equation. Okay, so how are we going to deal with this in terms of calculating what the question is asking for, which is the molar solubility, right? So what we're going to do is we're going to start off with initially, again, a nice table. Hope I can fit it here. Where initially, we won't worry about this because that's a solid. Here, it will be 1.50 M, which is the molarity of the ammonia that we're beginning with. And then the concentration of the complex would be 0, and that of the bromide ion would be 0 as well. The change here would be minus X here for minus, oh, I'm sorry. So if we're going to assume that the change, let me clear this here. If we're going to assume that the change for the complex and the bromide on the other side is plus X here and plus X here, then the change as far as the ammonia is concerned is minus 2X, right? So that at equilibrium, you're going to have 1.50 minus 2X, and here you're going to have X, and here you're going to have X, right? And of course, what we can do is plug these values into the expression for K for this reaction, which is the concentration of AgNH3 2 plus times the concentration of Br minus divided by the concentration of NH3 squared, right? So we have to put these terms in. I'm going to need more space, so let me erase up here. So when we plug in the values for Kf, that will be equal to, or the terms for Kf, that will be equal to X squared, because you're going to have, this is X from down here. So X squared divided by 1.50 minus 2X all squared, right? And basically from here, that will equal to 9.04 times 10 to the minus 6, which is what we have here for the K for the reaction. And therefore from here, it's basically algebra. So basically what I would do, since I have X squared here and 1.50 minus 2X squared, I would find the square root of both sides, right? So when we do that, you're going to end up with X over 1.50 minus 2X equals to the square root of 9.04, 9.04 times 10 to the minus 6. So if I find the square root of that, I got 3.01, right? So to solve for X, let me erase down here. Just some more algebraic steps. that we have to do. So we're gonna get, when you cross multiply, you're gonna get x is equal to 3.01 times 1.50 minus 2x. And then the next step is, oh, sorry, 3.01 times 10 to the minus 3. Can't forget that, 10 to the minus 3. So let me change this down here. So 3.01 times 10 to the minus 3 times 1.50 minus 2x. And then the next step is we distribute, so 3.01 times 10 to the minus 3 times 1.5, and that gives you 4.52 times 10 to the minus 3 minus, and then 2 times 3.01 times 10 to the minus 3. So that gives 6.02. 02 times 10 to the minus 3 x. All right. So remember, the aim is to solve for x. Let me erase down here.
Where did we get 6.02 times 10 to the negative 3?
By multiplying, oops. By multiplying 2 by 3.01 times 10 to the minus 3. Right. Okay, so to bring like terms on both sides, what I'm going to do is add 6.02 times 10 to the minus 3x to both sides. Right? So these two will disappear. Now, this is 1x plus 6.02 times 10 to the minus 3. So that's in 6.02 times 10 to the minus 3 is a very small number. So basically, this will be the same as x equals to 4.52 times 10 to the minus 3. And that would be equal to, if you remember the ice table that I had before, which I erased, that would be equal to the concentration of Ag plus, right? And the question was asking for the solubility, which would be X. So this would be also equal to the solubility of AgCl, of AgBr, I'm sorry, in 1.50 m ammonia, right? Because if you remember from the ice table that I drew earlier, the X is the solubility of the AgBr. So therefore, which would be equal to the concentration of silver ions. So once we got the concentration of the silver ions, then that would automatically be equal to the solubility of the AgBr. And the units here would be M, all right? Yes, sir.
So when you add 6.02 times 10 to the negative 3 plus 1x, that's equal to x?
Yeah, because 6.02 times 10 to the minus 3 is very, very small compared to 1. So it's like adding 0 to 1. Same difference. All right? Okay, any other questions? Any other questions? Any other questions out there in Zoom? Okay, so what we have done now is answered. Remember now, this is the B part. So now we need to do the C part. And the C part is asking what mass of silver bromide will dissolve in 175 mils of the 1.5 m ammonia. So to answer that, we have to, of course, recognize that the solubility is what we just calculated here. Let me erase down here. So basically, it's all a matter of taking the 175 mils of solution, converting it to liters. So 175 mils of the solution, we're going to convert it to liters. 1 liter over 1,000 mils of the solution. And then we multiply this by the molarity that we just calculated here, which is the 4.52 times 10 to the minus 3 moles of silver chloride divided by 1 liter of solution. And then we, you know what, let me make this more clear. I think I jumped a step. This would be the moles of silver ions over 1 liter of solution. And then now the next conversion factor is that you're gonna have 1 mole of silver ions down here, which is equal to 1 mole of silver chloride above. And then the last step is where we multiply the moles here of silver chloride by the molar mass. So that would be 1 mole of silver chloride down here. And the molar mass, of course, you can get from the periodic table. I think I have it here as 187.77 grams of silver chloride. And that's the setup. So this thing keeps.
You're doing chloride.
Is it silver bromide?
I mean bromide. I keep saying chloride. Silver bromide. Let me make that clear here. Silver bromide, bromide, bromide. All right. Okay. So this will cancel with this. This will cancel with that. That will cancel with that. That will cancel with that. So the only unit here remaining will be grams of silver bromide. So when you do the number crunching, 175, whoops, 175 divided by 1,000 times 4.52 times 10 to the minus 3 times 187.77. And according to my calculation, when rounded off to 3 sig figs, the answer becomes 0.148 grams of silver bromide. And that's how that is done. All right?
Why would it be 3 sig figs?
I'm sorry? Why would what?
Would it be 3 sig figs?
It is 3 sig figs. 148?
No, well, why would it be?
Why is it? Because you have, to begin with, you have 3 sig figs here, 3 sig figs here, and more than 3 sig figs here. The other numbers are exact numbers, so you round off according to the lowest number of 3 sig figs.
4.5 what times 10?
4.52, it should be a 2 here.
Oh,
Yeah. All right. Okay, any other questions? Yes, sir.
How come we don't use 1.5 layers of NH3 from?
Well, because the question says, well, the main reason why is because the silver ion is the limiting reactant in this case. So therefore, the ammonia is in excess. And if you remember from your Chem 1, it's a limiting reactant that determines, you know, the product outcome. And in this case, determines the solubility of the silver bromide. All right? Okay, any other questions before we move on? So this is the last question, right? We're basically finished with this chapter. So no questions, no more questions? All right, so let me clear this. And that's the last question. So let's see here. Nothing much else to cover as far as the PowerPoint is concerned. I will leave you to read up on this section right here. For those of you enrolled in my lab, you'll be doing something like this at the end, at the very end, the last 3 lab periods, where you will be identifying unknowns using separation of ions and so on. So this is pretty straightforward. If you follow this, if you can read this, that would help in terms of understanding how this process works. So I'm going to leave that for you to read upon. If you have any problems or questions about this, feel free to contact me about that. And then this is just basically talking about ion test. I don't know, flame test for cations. I don't know if you guys have come across this before, but basically you can use certain flame tests to determine the presence of certain ions. All you have to do is take an inert wire, like nichrome wire, dip it in your solution which contains ions, and then you insert it into the Bunsen flame, and different colors will indicate the type of ions that are present. So these are just some examples of the flame colors that result from the presence of the ions listed underneath. And that's all that basically is talking about there. And this is just basically talking about some reactions which is associated with the formation of calcium carbonate, which is the composition of eggshells. So nothing much there to talk about. All right, so that's basically it for this chapter. So now we're going to move on to the next chapter, which deals with thermodynamics. So let me go to files and lecture notes. Thermodynamics. You know what? Let me publish it first. Then open it up. Okay, so in Chem 1, you should have been exposed to the topic of thermochemistry, which basically deals with enthalpy changes, right? And of course, you would have learned terms like exothermic reactions and endothermic reactions and Hess's law and all that good stuff, right? So this chapter is basically an extension of that, all right? Because there's some other terminology that you'll be introduced to as it relates to energy changes in chemical reactions. Okay, let's see what's happening here. All right, so let's start off with a discussion. Oh, shoot, why did I do that? Okay, so let's start off with a discussion of this term, spontaneous. Now, that term, spontaneous or spontaneity, means something different when it comes to thermochemistry as opposed to everyday language. You know, the word spontaneity in everyday language, you know, conveys this idea of something, you know, spectacular happening or something like an explosion or something like that, right? In chemistry, physics, and so on, this is not actually the case, right? The term spontaneous refers to a process where basically it occurs, that process will just naturally occurs without any external intervention on anybody's part, right? So here are some examples of some spontaneous processes, right? Water running downhill, right? That will just simply happen. You don't have to do anything to make it happen, right? A lump of sugar dissolves in a cup of coffee. Again, that's another example of a spontaneous process. That will just simply happen without you doing anything. All you have to do is add the sugar to the cup of coffee and it happens, right? At 1 atmosphere, water freezes below 0 degrees and ice melts above 0 degrees. Again, those are two examples of spontaneous processes. Heat flows from a hotter object to a colder object. Again, spontaneous, right? If you have a gas that expands in an evacuated bulb, another example of a spontaneous process. And then this one, which is a more slow process, but it's still spontaneous, iron exposed to oxygen and moisture to forms rust, right? So these are all examples of spontaneous processes. So if you look at the picture here of somebody going down the hill sliding down the hill, that's a spontaneous process. That person literally don't have to do anything in order for that to happen. Now, to go the other direction, that would be a non-spontaneous process. And usually energy would have to be expended in order to carry out a non-spontaneous process, all right? So as stated here, spontaneity is basically dealing with the issue of whether or not a process will occur unassisted, all right? So here's another example of a spontaneous process. So imagine, if you will, you have two vessels that are connected by a stopcock, which basically does not allow, if it's closed, does not allow the gas trapped in one half to go into the other half, right? And we all know what's going to happen. If you open the stopcock here, right, the gas from the left side will simply flow into the right side, right? So this is a spontaneous process because it happens, you know, on its own without any external intervention. The opposite is not spontaneous, right? In order for you to have all the gas going back into one container, something would have to be done on your part in order to make that happen. So basically, usually that means that some energy would have to be expended in order to drive a non-spontaneous process, all right? Okay, so this begs the question, can we make a prediction, especially when it comes to chemical systems? Can we make a prediction as to whether or not a reaction is going to be spontaneous? Because as you all should know by now, the fact that you can write down an equation for a reaction doesn't necessarily mean that the reaction will occur, right? So people have been looking at, you know, different reactions and the fact that they're spontaneous and what makes them different compared to non-spontaneous reactions. So these are just some examples of spontaneous reactions. And what has been observed consistently is that most spontaneous reactions are exothermic, such as in the case of these two. Now, the ones that are endothermic, usually the delta H values are relatively small, such as these two, all right? So without knowing anything else, right, we can come to the conclusion that most spontaneous reactions are exothermic, but those that are endothermic, when you measure their delta H values, they're usually very small, right? So I think I have a summary here. There are two factors that drive any spontaneous process. Enthalpy, right, which as I said before, most of them are exothermic, but you have a few that are endothermic, but the delta H value is small and positive. But there's another factor that would make a reaction or that would influence a reaction to be a spontaneous reaction. And that factor is called entropy, right? So you have enthalpy, which is one factor, and then you have entropy, which is another factor. So what is entropy? Well, admittedly, this is a simple definition. There's actually the definition, the actual real definition of entropy is a bit complex, all right? You'd have to delve deeply into chemical thermodynamics in order to get that definition. But for our purposes, we're going to work with this definition right here, right? So this definition says entropy, which is symbolized, by the way, the letter S. That's a symbol that is universally used for entropy. It's a measure of the degree of randomness or disorder in a system, right? So the more disorder the system is, the greater would be the entropy, right? Or the other way of saying it, the more ordered the system is, the lower would be the entropy. The greater the disorder, then the greater will be the entropy, all right? So that's what entropy is for our purposes. It's a measure of the degree of randomness or disorder in a system. So you can actually measure the entropy of different systems, right? And if you have a system undergoing a change, right, then the change in the entropy would be the final entropy value minus the initial entropy value, right? So this is similar to what you'd have learned in thermochemistry where it comes to delta H or when it comes to delta T, right? It's the final value minus the initial value. Same is true for entropy. The final value of entropy minus the initial value of entropy, that would be the change in entropy. And you can have a situation where the change in entropy is positive or negative. So if the final value of entropy is greater than the initial value, then delta S would be positive, which corresponds to an increase in the amount of disorder or the increase in entropy. All right? Now, we can make qualitative predictions as to what the change in entropy is just by using our imagination and considering the nature of the different states of different substances involved. So for example, if you have a solid state substance, like let's say ice, right? And you heat it until it melts, it becomes water, right? And we all know that the structure of ice is more ordered compared to water, right? Because the ice structure have molecules in fixed position relative to each other. Water, the molecules are more randomly moving around, right? So basically we can conclude, just basically, on that knowledge, we can come to the conclusion that the entropy of water is greater than the entropy of solid ice, right? And then further, if you were to heat the water to vaporize it to form water vapor, again, using our imagination, we know that water vapor molecules have a more random motion compared to the water in a liquid state, right? So we can conclude that the water vapor would be of a greater entropy compared to water in a liquid state. So basically, this is the relationship between the entropies of anything in a solid state compared to the liquid state, compared to the gaseous state. And as I said before, these values can be measured. And when you see these values, you're going to see basically what we observe here. The entropy of the gas would be greater than the entropy of the liquid, which in turn would be greater in value than the entropy of the solid, all right? So this is the water example here from solid to liquid. Delta S is going to be positive, and it can be measured. There's actually a value that's attached to that transition, right? And here are some other examples, right? So we talked about the solid to liquid, liquid to gas, right? In both of these cases, delta S will be positive. But let's consider, for example, dissolving a solute in a solvent, right? So let's say, for example, you're dissolving sugar in water, right? Sugar is a solid, has a more ordered structure in terms of how the molecules are arranged. But when you add it to water, right, then basically the sugar molecules will dissolve. More random motion will be associated with the sugar molecules in that state. So therefore, the entropy increases as you go from the original solute and solvent to the solution. So therefore, delta S will be positive. And even within the same state, right, you can have an increase or decrease in entropy. So let's say you have a piece of metal like iron, right? And let's say that the temperature of iron was 26 degrees, right? And then you heat it to, let's say, 75 degrees, right? Now you might be saying, well, it's still iron, right? It's still solid iron. But what's going to happen at the microscopic level is that at a lower temperature, the atoms will have a certain amount of vibration around a particular equilibrium position. And if you were to heat it, that frequency of vibration would increase, right? That represents an increase in entropy, right? Because the hotter iron, which has a greater frequency of vibration of the atoms, will be more disordered compared to what is happening at a lower temperature. So basically, any system that you're increasing the temperature of will have associated with it an increase in entropy. Okay, so based on what we have just discussed, let's see if you understand what the entropy change would be for each of the following processes. Condensing water vapor. Now remember, condensation is where you're going from, you're going from H2O gas to H2O liquid, right? So would that correspond to an increase or a decrease in entropy? Decrease, exactly. And that's because of the decrease in randomness, so therefore, delta S is going to be negative. Okay, the next one. Forming sucrose crystals from a super saturated solution. Would that correspond to an increase or a decrease in entropy? You're going from solution to crystals.
Decrease,
What's that?
decrease,
Decrease. Correct. Okay, next one. Heating hydrogen gas from 60 degrees to 80 degrees. Increase, exactly. All right, and I think I have one more. Subliming dry ice. So just in case you don't know, dry ice is frozen carbon dioxide. And sublimation is where you're going from CO2 gas, I'm sorry, CO2 solid to CO2 gas. So what is the change in entropy? Would that be an increase or a decrease? Increase. So the answer is an increase in entropy, right? And I think that's the last one. Okay. Now, before we move on to the next topic, let me get you started on assignment 6. And please forgive me for how this is stapled to the side. I didn't realize that happened until after I printed out copies from the copier. Just like I pressed the wrong button while I was doing this. It's before me. Okay, so let's deal with the first question. In each of the following, I can't forget my folks out there in Zoom. Sorry, folks out there in Zoom. Let me see if I have published this in Canvas. We go here, okay, and then Files. Assignments. This is assignment number 6.
I didn't go.
Oh, sorry. Okay, so for you guys out there in Zoom, you should now be able to access assignment number 6. And let me clear this. Okay, so number 1 is basically asking for something similar, but this time what they're doing is giving you pairs of formulas, and you're to tell, or compounds, and you're to tell whether or not which one has a higher entropy. In other words, which one is more disordered, right? So what say you is the answer for 1A? H2S liquid versus H2S gas. Which one is more disordered?
Yes.
H2S gas, right? Very good. What about B? Sodium gas and sodium solid. Sodium gas again, exactly. C, H2O gas at 150 degrees Celsius and H2O gas at 200 degrees Celsius. 1 at 200 degrees Celsius, right? And then the final one, sugar as a solid and sugar dissolved in a cup of water. Exactly. So basically, that's it, right? The one that's more disordered has a higher delta S value. Okay, let's go back to the PowerPoint. So entropy is a state function. And if you recall from your Chem 1, General Chem 1 chapter dealing with thermochemistry, you should have met this definition of state function, right? State functions are properties that are determined by the state of a system, regardless of how that condition is achieved, right? And we have different examples of state functions that you'd have met before. Energy, enthalpy, pressure, volume, temperature are all state functions. And entropy that we have just learned about is also a state function. So basically, the change in entropy that one could determine from a system undergoing, let's say, a chemical change, that change is independent of how you get from the initial state to the final state, right? And the analogy being used here is 2 hikers starting from the base of this mountain. One hiker decided to go this path, the other one decided to go the red path, but it doesn't make a difference. They achieve the same goal of getting to the apex. So therefore, the difference in the height, which is basically an analogous to the state function, is the same regardless of the path that each person took, all right? So that's basically true also for entropy. Now to the left, or I should say to the right of this page, you'll see some values of entropy for different substances. So as I said before, entropy can actually be measured, right? And we can confirm what we said about the difference in entropy values between solid, liquid, and gas, right? As we said before, gas would have a higher entropy value compared to liquids, which in turn would have a higher entropy value compared to solids. And we can see that clearly when we compare H2O, for example, gas to liquid. The value for H2O gas is 188.7. And by the way, this is a unit of entropy, joules per Kelvin mole, right? So the value for H2O is 188.7. The value for H2O liquid is 69.9. So you see there clearly that the gaseous state will have a greater entropy value associated with it compared to the liquid state. We can see that when you compare bromine gas and liquid, iodine gas and solid, and so on and so forth, all right? Again, I've provided for you guys a more comprehensive table with these values in Canvas. Let me see if I can show you where it is. So if you go to tables, and where it says thermodynamic data, all right, so this is a bit more comprehensive table. It gives you, let me just show you. Okay, so it gives you in the extreme left side of the column, it gives you the formulas of different substances. Here it gives you the enthalpy of formation values. This you'd have met before in general chemistry 1. And then to the extreme right, you have the corresponding entropy values. All right. And this middle column, we're going to use it later on. This contains information known as the free energy of formation. All right. We're going to talk about that later on. But for now, this is basically what we're going to use to determine the change in entropy. And pretty much, if you remember what you did when it comes to determining the enthalpy of a reaction, right? Using the enthalpy of formation values of different substances. It's pretty much the same approach when it comes to using entropy to determine the entropy of a reaction, right? You can use the individual entropy values of the different substances to determine the entropy change of a reaction, all right? So we're going to see that shortly, actually. So let me see here. Next thing we need to talk about here is the first law of thermodynamics. You should have met this before. Energy can be converted from one form to another, but energy cannot be created nor destroyed. And then, which you have not, I don't think you have met this before, second law of thermodynamics, which says that the entropy of the universe increases in a spontaneous process and remains unchanged in a process that is in a state of equilibrium, all right? So basically what they're saying here is that for a spontaneous process, the entropy of the universe will increase, will be greater than 0, right? Or the change in entropy of the universe will be greater than 0. The entropy of the universe is basically, simply put, the entropy change of the system plus the entropy change of the surroundings, right? So this is what happens in a spontaneous process. In an equilibrium process, it turns out that the entropy change of the universe would be equal to 0, right? So basically, there will be no change in entropy of the universe if the system is in a state of equilibrium. And that's basically what the second law of thermodynamics is saying. Okay, so let's get back to entropy, and we can define what is called the standard entropy, which is the entropy change for a reaction carried out under the conditions of 1 atmosphere and 25 degrees Celsius. Again, this should be something that you would have met in general chemistry 1 when it comes to the standard enthalpy change of a reaction. The same conditions will apply, 1 atmosphere and 25 degrees Celsius. So if you have a hypothetical reaction, such as the one shown here, to calculate the entropy change, basically it's the sum of the total entropy change of the products minus the sum of the total entropy change of the reactants. Very similar to what you learned in Chem 1. In the case of Chem 1, you learned it in terms of the enthalpy change. The total sum of the enthalpy change of the products minus the total sum of the enthalpy change of the reactants would be equal to the enthalpy change of the reaction. In the case of entropy change, similar, right? Total sum of the entropy values of the products minus those of the reactants. Of course, you should be familiar with what this small 0 or O is as a superscript that represents standard conditions, 1 atmosphere and 25 degrees Celsius, right? And basically all you have to do is look up into the table that I just showed you and plug the numbers in, right? Another thing you need to remember is that you need to multiply those values by their corresponding coefficients, right? So for example, in the case of C here, right, you look up the value of the entropy of C and multiply by its coefficient, which is lowercase c, right? And the same is true here, and the same is true right throughout the equation. So let's apply that to this example. This question says, what is the standard entropy change for the following reaction at 25 degrees Celsius? And it gives you the equation of the reaction, right? So basically, you have to go to the tables and you have to look up the entropy values, the standard entropy values of the different components or the different substances involved. For carbon monoxide, it's 197.9. It's for oxygen, 205.0. And for carbon dioxide, it's 213.6. And basically, you plug those values into the equation. Now remember, it's the product minus the reactants. And remember, you need to multiply each of these values by their corresponding coefficients. So when you plug them into that equation, you're going to get 2 times the entropy of carbon dioxide, which is the product, minus the sum of 2 times the entropy of carbon monoxide plus the entropy of oxygen. And you plug the numbers in, and then whatever results would be the answer. And that's basically what you do in order to calculate the change of entropy in a reaction. All right? Okay, any questions about this? Any questions? Okay, so A couple of things that we can say about entropy changes, especially when it comes to the sign of entropy, right? Again, you can use your imagination to figure this out, right? So let's say you're asked a question. Let's say you're given an equation and you're asked whether or not the entropy is negative or positive. Right? You're not being asked to calculate it, just whether or not delta S is positive or negative, right? Basically, if you have a reaction where gases are produced or consumed, then if the reaction produces more gas molecules than it consumes, then delta S will be positive, right? So if you compare both sides of the equation, you have more gas molecules on the right side compared to the left side, then you can come to the conclusion that delta S is positive without doing any calculations, all right? If the reverse is true, right? If you have more gas molecules on the left side of the equation compared to the right side, then delta S, of course, will be negative, right? Now, if there's no net change in the number of gas molecules, then you cannot make a prediction without doing calculations, right? So at best, you can say that delta S may be negative or may be positive, but you can rest assured that it's going to be a very small number, right? So you cannot predict whether or not delta S would be positive or negative if you have identical number of gas molecules on both sides, right? The best you can say is it's going to be a small number. It may be positive or negative, but it's going to be a small number, all right? So let's look at this example here, right? It gives you the equation, the balanced equation, which is important. And the question is asking for the sign. It's not asking for you to calculate. It's just asking as to whether or not delta S is positive or negative. So what do you think the answer is? Will be negative. Why? Because?
For gas molecules.
Right, you have one oxygen molecules on the left, you have no gases on the right, right? So therefore you'd expect delta S to be negative, right? Okay, so that's basically what you look for in order to make predictions when it comes to gases being involved, right? Okay, so if you have an exothermic process occurring in a system right here, which means that it's generating heat, and if the heat can pass through the walls of the container, then basically the heat will be transferred to the surroundings. The result of that is that the entropy of the surroundings will increase, right? So delta S will be positive. And then in the case of an endothermic process, the opposite is true. The entropy of the surroundings will decrease, all right? Okay, and then let's talk about the third law of thermodynamics, which says the entropy of a perfect crystalline substance is zero at absolute zero of temperature, right? So basically what this law is saying is that if you're able to cool down anything to 0 Kelvin, then you will have the formation of what is known as a perfect crystalline substance, right? Now, the thing is that absolute zero has never been achieved. And up until this morning when I checked, that is still true, right? Nobody has achieved absolute zero, right? What I read this morning was that they came very close. If I remember correctly, it was 38 picokelvin of zero or close to zero, but they have never achieved zero, right? So this concept of crystalline, perfect crystalline substance at 0 Kelvin is a purely theoretical concept which has not been proven or disproven yet. But basically, it's a prediction based on certain mathematical approaches that have been used to determine or predict what would happen if you could achieve 0 Kelvin. All right. Okay. So as you can see here, and of course, we're familiar with what happens when you heat a substance from below the melting point, then it melts, becomes a liquid, and then you heat that liquid further, then it boils, and then becomes a gas, right? So if you plot the temperature in Kelvin versus the entropy, this is basically what you're going to observe. So the entropy increases as the temperature increases, all right? Okay, so back to the assignment. Okay, so where is it? Okay, so the next question, it says, using the tables provided in Canvas, calculate the entropy change for each of the following, right? So you're going to need the tables, you're going to need that table in order to answer this question here, or these questions, right? So let me Okay, so for the first one is carbon graphite going to carbon diamond, right? So you have to look up the entropy, standard entropy values for diamond. So in the interest of time, I've done that already. So in the case of diamond, the value is, when you look it up, 2.377 joules per mole Kelvin. And in the case of graphite, it is 5.740 joules per mole Kelvin. Right? So delta S standard would be equal to 2.377 joules per mole Kelvin minus 5.740 joules per mole Kelvin, right? And according to my calculation, this works out to be minus 3.363 joules per mole Kelvin, right? So that's it, right? Total entropy of products minus total entropy of reactants, and that's it, right? So basically, I'm going to leave the rest for you to do in question number 2 because it's pretty much the same thing. All you have to do is look up the values in the table and do the products minus reactant thing, and that's it. Any questions about this? Any questions? Any questions? All right, let me clear this. So you should be able to do, based on what we have done, B and C and D. And I want to look at now question number 3. So question number 3 says here to calculate the standard entropy change for the formation of gaseous propane. And this is the equation given. So again, you have to consult the tables. Let me see what I have here. Right, so you have to consult the tables. So in the case of propane, the value is 270.2 joules per mole Kelvin. In the case of graphite, it's 5.740 joules per mole Kelvin. And in the case of hydrogen, it's 130.68 joules per mole Kelvin. So delta S standard would be equal to 270.2 joules per mole Kelvin minus the sum of 5.740 joules per mole Kelvin plus 130.68 joules per mole Kelvin. And according to my calculation, this works out to be 269.7 joules per mole Kelvin. And that's it. Yes, sir.
You like multiply the coefficients.
I'm sorry?
Like, don't you multiply?
Oh, yes, you need to multiply. Thank you. So in the case of carbon, that would be 3 times this. And in the case of hydrogen, that would be 4 times this. Thank you very much. But the answer is still this. Okay, any questions about this one? Any questions? Okay, we can't do number 4, so back to the PowerPoint we go. Okay, so let me clear this. Back to the PowerPoint. So now we're going to get into how do we actually predict whether or not, excuse me, a reaction is spontaneous. Remember we said that one of the things that we saw that is common with spontaneous reactions is that delta H is negative, right? And if it is positive, it's a small number, right? But we need something more definite in order to be able to make predictions as to whether a reaction is spontaneous. So this leads us now to a discussion of what is known as the Gibbs free energy, which is represented by delta G. The definition of the Gibbs free energy is the energy associated with a chemical reaction that can be used to do work, all right? Now, for a constant temperature process, so assuming that the temperature is constant, we now have a relationship between the enthalpy of a reaction and the entropy of a reaction and the Gibbs free energy, and that is this equation right here, right? So the Gibbs free energy is equal to the change in enthalpy of the reaction minus T times the change in entropy, right? And it is this delta G that helps us to determine whether or not a reaction, as it is written, is spontaneous, all right? So basically, if delta G is negative, right? So you plug the values of delta H, T, and delta S into that equation. If delta G is negative, then that means that the reaction is spontaneous in the direction as written, right? If delta G is positive, that means that as the reaction is written, or as the equation is written, the reaction is not spontaneous. Instead, the reaction is going to be spontaneous in the reverse direction, all right? And then if delta G is equal to 0, that means that the reaction is at equilibrium, right? And the consequence of that is, based on this equation here, is that if delta G is 0, that means that if this is 0, therefore that means that delta S would be equal to delta H divided by T, right? So at equilibrium, this would be the case. Delta S is equal to delta H divided by the temperature, which, by the way, must be in Kelvin, all right? In fact, in all of these equations where temperature occurs, must be in Kelvin, all right? So that is the relationship between the free energy, delta H, T, and delta S, and we can use this to predict whether or not a reaction is spontaneous, all right? Now, the delta G value under standard conditions for reaction, it's the energy change or the free energy change where the reaction is conducted under standard state conditions. And here we have a small table here, which gives you the conditions. 1 atmosphere pressure for gases. If it's a liquid, it's a pure liquid. If it's a solid, it's a pure solid. And for elements, delta G standard of formation will be 0. And if there are any solutions involved, then the concentration of the solution would be 1 molar, right? So if you have a reaction, again, a hypothetical reaction, such as the one that we saw earlier, we can calculate delta G standard pretty much in the same way as we done for delta S and for delta H, right? It's a sum of, in this case, the total free energy standard for the products minus those for the reactants. And going back to the same table I showed you, the middle column is what contains the standard enthalpy of formation, standard free energy of formation, which is this middle column right here in this table, right? So this is where all the delta G values of formation of different substances are located. And you'll notice that one thing it has in common, the delta G values, one thing they have in common with the enthalpy values is that for free elements by themselves, right, their values are automatically 0, right? So if you look at aluminum here, the free energy of formation of aluminum is 0. Same thing for enthalpy of formation. And if I were to scroll down, you see the same thing for arsenic, same thing for barium, scrolling down, same thing for boron. All elements by themselves have a free energy value standard of formation equals to 0, all right? So that's as far as free energy of under standard conditions are concerned. So let me go back to the PowerPoint and see what's on the next slide. Okay, so this is basically the equation, as I said before. And this is the point I made just now, right? The free energy of formation of elements in the standard form is 0. All right, so based on what we have just learned, we can do a question like this one. It says, what is the standard free energy for the following reaction? And this reaction is basically the combustion of a compound known as benzene, right? So again, same approach. It's sum of the free energy standard of the products minus sum of the free energy standard of the reactants, right? So basically, we have to take into account again the coefficients, the 12 and the 6 for the carbon dioxide and water, and the 2 for the benzene. And you'll notice that they did not include oxygen. Why? because oxygen is an element by itself, right? So remember what I said. Any element by itself, the free energy is zero. So therefore, there's no need to include oxygen here. So all we have to do now is consult the table to look up the values for carbon dioxide, water, and benzene, and plug those numbers in, and you're going to get delta G for the reaction, which is minus 6,405 kilojoules. All right? And that's it, right? That's basically how you determine the free energy of a reaction if you know what the free energy standard of the different substances are. Now, here's another question being asked in relation to the same reaction. Is this reaction spontaneous? And what say you? Is this reaction spontaneous? What did we say about the spontaneity of a reaction as it relates to delta G?
It's negative, it's spontaneous in that direction.
Exactly. So it's negative 6,405. So that means that the reaction is spontaneous. All right. Okay. Very good. Any questions about this? Any questions? Yes, sir.
What does it mean by in the reverse direction?
Meaning if you're going from the other direction. So if you have this reaction going in this direction, right? Delta G is negative, is spontaneous. Which basically means that the reaction will just take place by itself without any external intervention, right? Now, if you're trying to react carbon dioxide and water to form these products or these reactants, then delta G would be positive because that would be a non-spontaneous direction under those conditions, all right? Which means that it will not occur unless you do something to make it happen, all right? Okay, so let's look more closely at the relationship between delta G, delta H, T, and delta S, right? So basically, as she just said, delta G being negative would mean that the reaction would be spontaneous going in the forward direction. Delta G being positive would mean that the reaction would be spontaneous going in the reverse direction, all right? So what we're gonna look at here is how the signs of delta H and delta S will affect outcomes in terms of delta G being negative or positive, which therefore will tell us whether or not the reaction would be spontaneous or not. So let's look at a situation where delta H is positive and delta S is positive, right? So imagine, imagine delta H being positive and delta S is positive, right? So the question is, what would be the sign of delta G? Well, the answer is, it depends. And what does it depend on? It depends on the temperature. It depends on how large or small the temperature is, right? So as stated here, if the temperature is high, right? So imagine this. If this is high, while this is positive and this is positive, that means that delta H would be less than T delta S, right? So therefore, that means that if delta H is less than T delta S, what does that mean for delta G? Delta G would be what? If delta H is less than T delta S, then delta G would be what? Negative, which means that the reaction will be spontaneous if the temperature is high, right? So that's why it says here, reaction proceeds spontaneously at high temperatures, right? Now, what if the temperature is low, right? If the temperature is low, erase this here. If the temperature is low, then that means that delta H now would be greater than T delta S if delta S and delta H is positive. So what does that mean for delta G? Let me erase this here. What does that mean for delta G? Delta G would be what? Positive, right? And therefore, the reaction would not be spontaneous in that direction. It's going to be spontaneous in the other direction. So that's why it says here, at low temperature, the reaction is spontaneous in the reverse direction, all right? So as you can see, just in the case of the first example, where delta H is positive and delta S is positive, it can be a spontaneous reaction, but it depends on the temperature, right? If the temperature is low, then delta H, or I should say delta G will be positive. if the temperature is high, then delta G will be negative, right? And therefore, the reaction will be spontaneous when delta G is negative and non-spontaneous when delta G is positive. Okay, now let's look at a different situation. Let me erase all this here. Let's look at a situation where delta H is positive, so this is positive, and delta S is negative, right? Now, the question is, what's going to happen to delta G? Now, remember, delta G is equal to all this here, right? Then what you'll find is that if this is positive and this is negative, it doesn't matter whether or not the temperature is low or high. Delta H is always going to be greater than T delta S, right? Because this is negative, that means that you're going to end up with negative times negative gives you a positive, plus something which is positive. So that means that basically delta G is going to be positive, which means that the reaction will not be spontaneous going from left to right. It will be non-spontaneous going from left to right, which means that it's going to be spontaneous going from right to left. So that's why it says here, the reaction is spontaneous in the reverse direction at all temperatures. Doesn't matter what the temperature is, right? The reaction is going to be spontaneous going in the reverse direction, right? Okay, so any questions about that? Any questions? Yes, sir.
But judging from the example, if you just look at the example, then it's gonna be non-spontaneous, but if you reverse that, then it's spontaneous.
Exactly. Exactly. Okay, so let's look at the next situation. Let me erase all this here. Oops. So, okay, the next situation is where we switch the signs from the previous one. So delta H is negative and delta S is positive, right? So the question is, what effect or what will be the result for delta G? Now, if this is negative and this is positive, that means that T delta S is going to be positive, right? And you have a minus sign here. So what does that mean? That means that delta G is always going to be negative. Doesn't matter what the temperature is, right? So therefore, if delta G is negative, that means that the reaction is going to be spontaneous going from left to right. Excuse me. So as stated here, delta G is always negative regardless of the temperature, and therefore the reaction will proceed spontaneously at all temperatures, all right? And then the final situation here, where both delta H and delta S is negative, all right? What will be the situation for delta G? Here, as in the case of the first example, it depends on the temperature, right? So let's look at where the temperature is high, right? If the temperature is high, that means that this part here will be large and negative. You're going to have a negative sign here in front. You're going to have this negative here. So basically, delta G in this case is going to be positive, right? So therefore, the reaction will be non-spontaneous going from left to right, which means that the reverse reaction will be spontaneous if the temperature is high, right? And then if the temperature is low, right, the reverse will happen. In other words, this part here, which is negative, will be larger in magnitude compared to this part, which will be positive along with this negative sign, which means that delta G is going to be negative, which means that the reaction will be spontaneous when the temperatures are low, right? So that's basically what happens when both delta H and delta S are negative, all right? So basically, as you can see, whether or not a reaction is spontaneous is not only a function of delta H and delta S, but also a function of temperatures in certain situations, especially if delta H and delta S are of the same sign, all right? So that's what happens in this case. Okay. Okay, let me see here if we can do any more of the assignment questions. Okay, going back to the assignment. Let's look at number 4. Whoops, not that one. Number 4. It says, write a balanced equation that depicts the formation of 1 mole of Fe2O3 from its elements. Again, I made a mistake here. This should be, I need to correct these and resubmit it in Canvas. This should be A, this should be B, and this should be C. All right, so please make a note of that. Okay, so the A part is asking for you to write a balanced equation which depicts the formation of 1 mole of Fe2O3. So in other words, you have the elements here, from its elements, by the way, that's what the question says, right? So the elements would be iron and oxygen. We all should know by now that oxygen exists in nature as a diatomic molecule, right? So that's why we write O2 here. And then the product is Fe2O3. Now, what the question is asking for us to do is balance it, but we have to balance it such that the coefficient here for iron 3 oxide is 1, right? So this is fixed at 1, which means that to balance it, we're going to need a 2 here, or we're going to need 3/2 here, right? And that would be the equation for the formation of 1 mole of iron 3 oxide, all right? Now, the next question is asking, what is the free energy of the formation of 1.00 moles of iron 3 oxide? So, of course, we have to calculate the free energy of formation, the free energy of this reaction. And basically, because iron and oxygen are elements by themselves, you can ignore it. So basically, the free energy of this reaction would be the free energy of the iron 3 oxide, which I've already looked up before. And that is equal to minus 742.2 kilojoules for every 1 mole of iron. Right? But let me erase this here. What the question is asking for is what happens when you start off with 1.00 moles of iron 3 oxide. So 1 mole of Fe2O3, 1.00 moles of Fe2O3. So this will cancel out with this. So the answer would be minus 742 kilojoules. Of course, we have to round off to 3 sig figs, and therefore that's it. All right? Any questions about this? Any questions? Any questions? Okay, let me clear this and move down to the B part. I'm sorry, the C part. What is the free energy when 454 grams of Fe2O3 are formed from the elements? So again, you're going to use the same value of the free energy of formation of 1 mole of iron that we used above. But we're going to start off with 454 grams of Fe2O3. And then we'd have to convert that to moles. So you're going to have 1 mole of Fe2O3. And down below here, you're going to have the molar mass, which I've calculated already to be equal to 159.69 grams of Fe2O3. And then I'm going to multiply this by the free energy of formation standard, which is minus 742.2 kilojoules over 1 mole of Fe2O3. So .454 divided by 159.69. Oops, can I do this again? 454 divided by 454 divided by 159.69 times 742.2 minus. So according to my calculation, we have to round this off to 3 sig figs. So that's minus 2110 with a decimal point here. No, actually no decimal point. And the units would be kilojoules, because this will cancel with that, that will cancel with that. So this would be the final answer. Right? Any questions about this one? Any questions? Yes, sir.
Going back to question 3.
Okay.
When I calculated the final answer, I got negative 269.7. The answer is supposed to be an absolute value of the standard entropy.
For number 3. What did you, oh, 3, hold on. Okay, what did you say you got?
So I got negative 269.7, which is the same answer, but it's just negative. And I think you have it in the bottom.
Let me see. Yeah, you're right. So this should be negative 269.7. Thank you very much. All right. Any other questions? Any other questions? Let me clear this here. And now we're going to move on to okay, I'm only going to do one of these. And based on that one, you should be able to do the others, right? So number 5 is asking for you to use the values of delta S standard and delta HF standard to calculate delta G. So basically what they're saying that you should do for this question is, based on the equation I introduced earlier, delta G standard is equal to delta H standard minus T delta S standard, right? Based on the delta H and the delta S you'd have calculated, plug those numbers into this equation and then find delta G, all right? So for the first reaction, oh, I just remembered. This one, okay, let's not do the first one. Because if I remember correctly, the table that you have don't have the value for PbCl2. So I'm going to scroll down. You don't have to do this question at all. You can scratch it, all right? So I won't be grading it in your when I grade your assignment. So I'm sorry?
On number 2D, it says the carbon chloride, but it doesn't, our table doesn't have that either.
Oh, it doesn't?
It has chloride and it has carbon, but it doesn't have it together.
Oh, okay, I'll look into that one. All right. Okay, thank you for telling me that. Okay, let me scroll down now to this one. All right. So let me. All right, so what we need to do first is find out what delta H standard is for this reaction. So we have to consult the tables and we have to look up the enthalpy of formation of all of these. But again, magnesium is by itself as an element, oxygen is by itself as an element, so those would have a value of 0 when it comes to the enthalpy of formation. So the only thing we need to look up is for magnesium oxide. So when I did that, I got minus 601.70 kilojoules per mole, right? Minus 0 plus 0, right? 0 for the magnesium and 0 for the oxygen. So this works out to be equal to minus 601.70 kilojoules per mole, right? So that one is relatively easier to deal with. Delta S standard is what we need to calculate next for the same reaction. Now in this case, we have to look up the values for the magnesium, the oxygen, and the magnesium oxide. So when I looked that up, I saw that magnesium has a delta S. So these are delta S values. Magnesium has a delta S value of 32.68 joules per mole Kelvin. Oxygen has a value of 205.14 joules per mole Kelvin. And magnesium oxide has a value of 26.9 joules per mole Kelvin, all right? So delta S now would be 26.9 joules per mole Kelvin minus the sum of 32.68 joules per mole Kelvin plus 205.14 joules per mole Kelvin. And then we work that out. And when when I did that, I got minus 108.3 joules per mole Kelvin. Let me recheck that.
She multiplied by half for the oxygen.
Yeah, this part will multiply by half. Thank you. Okay, so let me see, let me do that here. Just to recheck.
Will you subtract 269 joules per mole?
Hold on 1 minute. Okay, that's what I got. Okay, what were you asking?
Minus sign in between.
Yeah, right here. Yeah, that's it, yeah. So that's what I got when I just redid it. In fact, the only minor change I would make here is that I'd run this off to 4 joules per mole Kelvin, all right? So now that we have delta H and we have delta S, all we have to do now is determine delta G standard based on the equation here. So delta H would be equal to minus 601.7 kilojoules per mole minus 108 joules per mole Kelvin multiplied by the temperature. What's the temperature? Well, because these are standard conditions, the temperature will be 25 degrees Celsius, which would be the same thing as 293 Kelvin. So we're going to multiply by, oh, by the way, this should be 108.4. So we're going to multiply by 298 Kelvin. But there's one other thing we need to do, because you'll notice that we have kilojoules here and we have joules here. So we need to keep the units compatible, right? So we can either convert the kilojoules to joules, or we can convert the joules to kilojoules, which is what I'm going to do. So I'm going to multiply by 1 kilojoule over 1,000 joules here, so that the joule units will cancel out here and here. The Kelvin units will cancel out here and here. So you're going to end up with kilojoules per mole, which you can add to this, which is also expressed in kilojoules per mole. And let's see what that gives. So I'm going to work out what's within the parentheses first. 108.4 minus times 298 divided by 1,000. And then I'm going to put a minus sign in front of that and then add it or subtract 601.7 and let's see what that gives. Okay, so according to my calculation, I got minus 56 point, I'm sorry, minus 569. How many sig figs? 3 sig figs. So that's it, minus 569. And the units here would be kilojoules per mole. And that's how you would do that. All right. So if you understood what I just did, then you guys should be able to do C. Let me see what else is within that question. You should be able to do C, and that's it. So just follow the same process. Let me just say that, you know, I would say that the most tedious part of doing questions like these is searching for the values in the tables, right? So, you know, that's just something you can't avoid. But once you find the correct values, then all you have to do is do the products minus reactants thing, put the numbers in, and that's it. All right. Okay. Any questions about this one? Yes, sir.
Where did you get the 298 Kelvin?
Because the temperature is standard temperature, which is 25 degrees Celsius. Remember I said that standard pressure is 1 atmosphere and standard temperature is 298 Kelvin. I mean, 25 degrees Celsius, which is the same thing as 298 Kelvin. All right?
So does that rule not apply for oxygen
the gas when it's just the element by itself, where we just make it.
For delta H, yes, that would be 0 for oxygen. Yeah, for all elements that exist in their natural states,
Oh,
the free energy of formation, or delta H for that matter, of formation would be
that
0.
applies to the, was it negatives?
Yeah, exactly. Okay, any other questions before we move on? Let me see. What's next? Okay, we can't do that yet, so let me go back to the PowerPoint. Okay, so let's talk about the relationship between free energy and chemical equilibrium. So basically, we're going to make connections between what we just learned about free energy and what we learned a couple of chapters ago concerning equilibrium, right? And it turns out that there is a relationship between the free energy of a reaction and the reaction quotient given by this equation, right? So the free energy of the reaction is equal to delta G standard, which is the free energy under standard conditions, plus RT times ln Q, where Q is the reaction quotient, R is the molar gas constant, T is the temperature in Kelvin. And please note that the value of R that you'll be using is right here, 8.31 joules per mole Kelvin. And as I said before, Q is the reaction quotient. Now, if the system is at equilibrium, then delta G here, if you remember we said, is going to be equal to 0, right? So if we set 0 here, right, and the system is at equilibrium, remember now at equilibrium, Q is going to be equal to K, right? So if we put 0 here and we put K here, this is the equation we're going to end up with. 0 is equal to delta G standard plus RT ln K, which means that delta G standard is going to be equal to minus RT ln K. So here we have established a relationship between the standard free energy of a reaction to the equilibrium constant, all right? So this is a very important equation. I think this is one of the equations that's available in Canvas. So you don't need to memorize it, even though you probably should when you're doing problems and all that. But I think this is actually in that packet, all right? Okay, so let's look at a graphical representation of the relationship between free energy and equilibrium. So the first graph right here represents what happens when delta G is negative, and this is what happens when delta G for the reaction is positive, right? So just to explain what's happening here, the y-axis represents the free energy, while the x-axis basically represents the progress of reaction as you go from reactants to products, right? So basically, if you start off with your reactants, the free energy would fall and fall and fall. And by the way, in this particular situation, the reaction quotient would be less than K. And if you remember what we discussed when we were first introduced to the reaction quotient, remember we said that if Q is less than K, that means that in order for equilibrium to be achieved, the reaction would have to shift to the right in order to increase the value of Q so that it's equal to K. And that's exactly what's happening here, right? The reaction is going to shift to the right, and therefore the Q value will increase until it becomes equal to K, right? So this would be the minimum energy achieved at the equilibrium of this particular system, right? And then if you're going in this direction, basically the free energy would have to increase a bit more, but the final free energy of the products would be less than that of the reactants, right? So basically, that's what will be happening in terms of the energy changes of this reaction here if delta G is negative. Now, if delta G is positive, you can see that the appearance of the graph is basically a mirror image of the first one, right? So again, if you start from reactants, what will happen is that the reaction will, the energy will fall until you get to the minimum part here, and that would be the equilibrium position right here. And then if you continue, then the energy will fall, or I should say increase, until the free energy of the products will be greater than that of the reactants, which of course is the case when delta G is positive, right? So you'll notice that the equilibrium position here, in a case where delta G is negative, is closer to the products. In other words, basically the amount of products will be greater in terms of the concentration compared to the amount of reactants. In this case here, it's the reverse. The amount of products or the concentration of the products would be less than that of the reactants at the equilibrium position, right? So that's basically what we're looking at here in terms of looking at the relationship between the free energy versus the extent of the reaction, right? And this here is basically a summary, again, well, what I showed you before was a graphical representation, but this is a very short summary of the relationship between delta G standard and K, right? So because of this negative sign, that influences the relationship between the two, obviously, right? So basically, if K is greater than 1, then ln K will be greater than 1 and positive. So if this is positive and you have a negative sign here, that means that delta G would be negative. And what does that mean? That means that products are favored over the reactants at the equilibrium position, right? Now, if K is equal to 1, we know that ln1, right, is equal to 0, right? Which means that delta G would be 0. And what that means is that basically the products and the reactants are both equally favored. So pretty much you have equal amounts of products and reactants. And then finally, if K is less than 1, that means that ln K would be negative, which means that because of this negative sign here, delta G standard will be positive. And what that means basically is that at the equilibrium position, the amount of products in terms of concentration will be greater compared to the amount of reactants, all right? And then finally, believe it or not, we're finished with this chapter actually. We're going to look at one biological application of what we just discussed, all right? Now, what we're looking at here is basically a very simplified explanation of the formation of proteins, right? But we're going to simplify, we're going to break it down into basically the formation of a dipeptide from 2 amino acids. But this can be extended to larger molecules, all right? Now, and I'm quite sure you learned this in your biology courses, amino acids basically will link up with each other to form longer chains, right? So we're looking at 2 amino acids here. One is alanine and the other one is glycine, right? So they will link up together to form a peptide known as alanyl glycine, okay? Now, the thing about this reaction is that the free energy of that reaction is plus 29 kilojoules. In other words, by itself, it's a non-spontaneous process, right? So basically, if you mix alanine with glycine, nothing's going to happen, right? Because that's a non-spontaneous process. You have to do something in order to make that a spontaneous process, right? And the main thing that you need to do is to supply energy. Now, in biological systems, the energy is supplied as a result of the transformation of a molecule known as ATP. When it converts to ADP, it loses energy, and that energy is provided to basically facilitate the linking of the alanine to the glycine, right? But the question is, where does that energy come from? Where does the energy comes from that ATP will have so much of it that it can provide that energy to drive this reaction? And that energy comes from the conversion of glucose to carbon dioxide and water in the body, right? So basically, this is an exothermic process. This provides energy which converts the ADP molecules to ATP. So basically, the energy that is produced in this reaction is used and stored in the ATP molecule. And then that energy is basically used to drive this non-spontaneous reaction where the amino acids will link together to form your peptides or proteins, right? So we can look at it in terms of what we just learned when it comes to the thermodynamics. So basically what we're looking at is coupling this reaction here from ATP to ADP with this reaction here. And when we look at the free energy of that coupling, you'll see that delta G now is negative, which means that the coupling results in the spontaneous reaction occurring, which results in the formation of protein. Without that coupling, the reaction will not take place, because without that coupling, the conversion of the amino acids to peptides and proteins would be a non-spontaneous process. So this is a biological example which demonstrate pretty much what we have learned in this chapter when it talks about whether or not a reaction is spontaneous and how we can make a reaction that is initially spontaneous to become spontaneous, all right? Okay, and that's pretty much it for this chapter, right? So we're finished with chapter, the thermodynamics chapter. And in terms of, that was it. Oh, okay. All right, so what I'm gonna do next class is continue with the assignment. I think there's only one question actually, hold on. Actually, two questions, yes. So two more questions and then we'll be finished with this assignment. And then I'll be moving on to the next chapter, which deals with electrochemistry, right? And I'm quite sure you guys have seen a notice I've posted in Canvas concerning test number 2. I neglected to mention that I'll be, whatever you get from your, when you do that redo, whatever grade you get from that, I'll be taking off 15 percentage points off the top. Right, so the maximum you're gonna get if you do everything perfectly is 85%. All right, and that is due tomorrow. And I think that's all I have to say by way of announcement. So that's pretty much it. I'll see you guys tomorrow. Oh, this is not nice. It's due tomorrow, yeah.
Yeah, I got it.
And also, if you have not turned in some of the assignments, you still can turn it in, but you'll be losing points for that as well, so.
I'm gonna go with you.
No,
Okay.
I have to create one for you. When can you do it? Okay, tomorrow after class or before class? What time?
Anytime after.
Send me an email to remind me, because I'll forget, all right? So, send an email like this evening, so I'll remember to be here.
Thank you.
No problem. Yes, sir.
It's only for the 21st. But that's the about behind you.
What I did.
I don't know.
This is actually insane. Bro, if I was coach, I would pick your team.
What do you, or the interview?
So you put me with the number 5.
Be good.
Okay.
Just nice. What's up? No, I'm waiting on.
Okay, so. This one here. It's 23 hours ago, that's yesterday. So this one you're saying is not there?
No.
All right, and is that it? Is that the other one? Okay, I'll take care of it during lab.
And then also, I think on my assignment number 4, I think I got the wrong score on it.
All right,
I only missed like half a point.
okay, let's talk into that.
Okay.
Yes, ma'am.
So you're.
No, Monday from 8 to 11. Why? I can be if we can make it work. If when do you want to
Tomorrow.
what time? All right, no problem, because since I'll be meeting another student at that time, I can. But again, send me an email to remind me, right?
That'll be over Zoom.
It can be over Zoom or, oh, you want to be Zoom?
Or which is better.
It doesn't matter. I mean, if it's Zoom, what that means is that I would have to create a link if that's the case. But if in person, then, so it's all up to you.
I'll send you an email.
Yes, please.
Thank you.
All right, yes, sir.
I think I got the wrong grade for assignment 4.
CME Lab,
Lab?
yeah, we can take care of that.
Alright.
Yes, ma'am.
So the question that I mentioned earlier, this one,
Okay, yeah, you were saying,
so I found the,
oh, this is nice. You actually printed it.
I found one of them.
Okay,
I
so,
found the liquid, but not the gas.
oh, okay,
So is there a difference?
yes.
Okay.
The value is actually dependent on the state. What I'm gonna do is look up the value for the gas. And then I'll like announce it so that
Yeah.
you guys can have it to
Okay.
work with, all right? But thanks for letting me know.
Yeah. And
Okay,
then, do you have an extra assignment 60, so I can? I love the stapling, that was very
I-
random.
that was totally arbitrary mistake on my part because normally when I press the button, you said assignment 5,
6,
6?
the one that you just moved out.
Oh, here it is. Yeah, I mean, I just pressed the wrong button and it came out like that, so. You know.
Thank you.
Mhm.